Hello everyone, I'm Norman Waldberger. Welcome to Algebraic Calculus 2. Today's video is called the K-Poly Algebras and Truncations. We're going to move a little bit into abstract algebra. In particular, we're going to study this concept of an algebra, and I'm going to introduce an important new family of algebras, which we're going to denote by the term K-Poly, where K is a natural number. These things are, in some sense, sort of finite and bounded versions of the more familiar polynumbers, whose type is poly. And I remind you that one of our main aims is to try to get at these ongoing polynomials or polynumbers, which is a type of polyseries. Okay, so here's a regular polynumber, 4, 0, 3, minus 11. It's essentially just a list of numbers, but we know that this can be translated to the more familiar polynomial form, 4 plus 3 alpha squared minus 11 alpha cubed. Here is a more dubious kind of polyseries with a pattern that is kind of ongoing in some sense. 1, 4, 9, 16, and then there are 3 dots. So we're still wrestling as to, how do we bring this kind of object into being precisely. In particular, we really need to focus on the nature of these 3 dots. What does this actually mean computationally? Or to put it another way, how is a computer scientist supposed to understand what's going on here? Okay, but today we're going to go kind of in the opposite direction and become even more concrete, even more finite, even more bounded with these K-polys. So here is what a K-poly is. It's a list of numbers, for us rational numbers typically. In this case, 2, minus 1, 0, 5. But notice that in contrast with the sign for the poly, which is this horizontal bar on top and then a vertical one on the side, this one here has a bar on the top and on the bottom. Okay, so it's constrained in extent, and so the elements are 2, minus 1, 0, 5. And this is going to be a 3 poly because this is really of degree 3 here. And we're going to introduce a similar kind of notation like this. So we're going to call this 2 minus alpha 3 plus 5 alpha 3 cubed. So we're kind of introducing a variant of alpha that will apply in the 3 poly situation to capture essentially the same idea, but a little bit differently. And sometimes when we are wanting to be a little bit faster and avoid a subscript, we'll just use a generic epsilon. Okay, so we'll also write this as 2 minus epsilon plus 0 epsilon squared plus 5 epsilon cubed. Now, all of these things are algebras, okay? And so that's going to be a key point today, is to introduce you to this abstract algebraic object, an algebra. Okay, so what is the definition of an algebra? So for us, an algebra with identity, in the theory of algebras, there's also algebras without identity, but they're not as sort of central as these ones. So we're not always going to say it, but all the algebras that we're going to be working with always have an identity. So what is that? Well, it's first of all a vector or linear space over the rationals. Maybe it's called A. So it's a vector space. It's got elements that can be added and scalar multiplied, and the usual vector space properties hold. But in addition, there is a multiplication, say denoted A times B. And this multiplication has a number of properties. First of all, associativity is required. A times B times C equals A times B times C. Secondly, it should be distributive with respect to the addition in the linear space. So A times B plus C should be A times B plus A times C. And we use the usual convention that we do these multiplications first before we do the addition. And similarly, on the other side, A plus B times C is A times C plus B times C. And there's another kind of distributive kind of law that concerns itself with the operation of scalar multiplication in our vector space. So if we have 2 elements A and B, we multiply A by, say, number lambda. So lambda A times B. Well, that's the same as what you get when you multiply A by lambda B. And that's the same as what you get when you multiply A times B by lambda. So you can move these scalars around in the sort of obvious ways. And then there's the crucial property that there's an identity, and that means that this element 1, so a distinguished element in the algebra, has the property that 1 times a equals a times 1 equals a for any a in the algebra. Okay, so that's an algebra. Okay, so there's a quintessential example of an algebra. It's the central example in mathematics for an algebra, and that's the algebra of n by n matrices. Again, over whatever field we're working with, say over the rationals. So that is an algebra because you can add matrices, you can scalar multiply them, and crucially, you can multiply them. The various properties are holding, and the identity element is the n by n matrix, which has 1s down the diagonal and 0s elsewhere. And this crucially is a non-commutative algebra. Okay, so the commutativity is not a required property. This is a non-commutative algebra and plays a big role. It'll actually play a big role for us in the Algebraic Calculus 2 course. Now, some other ones that are also pretty familiar here are the complex numbers, which I'm going to call them C sub B, B standing for blue. Okay, so one way of defining the blue complex numbers, or the familiar ones, it's vectors, x, y, with the usual additive structure of row vectors. And then here is the multiplication. x1, y1 times x2, y2 equals x1, x2 minus y1, y2, and x1, y2 plus x2, y1. Now, this multiplication can be maybe elucidated by realizing that you can identify this vector xy with this 2 by 2 matrix. So this embeds the blue complex numbers inside the algebra of dihedrons, which is the algebra of 2 by 2 matrices, special case of these ones here. So xy is associated to the matrix xy minus yx, and then the multiplication of these ones here defined up here corresponds to the multiplication for corresponding 2 by 2 matrices. And importantly, this algebra is commutative, so it obeys this additional law that, say, z times w equals w times z. Okay, so there's two important variants to the blue complex numbers, namely the red complex numbers and the green complex numbers, and they are also algebras. So the red complex numbers consisting of vectors x, y with the usual additive structure, and here's the product in the red algebras situation. So x1, y1 times x2, y2 is x1, x2 plus y1, y2, and also x1, y2 plus x2, y1. And we can realize these red complex numbers or represent them by associating to the vector xy the 2 by 2 matrix xy, yx. So then the multiplication that's being recorded here is just a reflection of the matrix multiplication of those kinds of 2 by 2 matrices or dihedrons. And then there's another example, which is also sort of a relativistic kind of variant of this one. The green complex numbers also consisting of vectors x, y, but now the multiplication is very simple. It's just a pointwise multiplication. x1, y1 times x2, y2 is x1 times x2, y1 times y2. And here the association of the vector to a matrix is very simple. We just put x and y down the diagonal. So these are all three of them are algebras. Now, students of mathematics will be, of course, very familiar with the blue complex numbers because it's a field. So what is a field? Well, a field is like an algebra, but with more additional properties, and that has to do with inverses. Okay, so what makes an algebra a field is the property that pretty well everything, except for the zero vector, has an inverse. So let's define invertible elements. If A is an algebra with identity 1, then an element A in A is invertible precisely when A times B equals B times A equals 1 for some B in A. And here we are adopting the more usual convention that we don't always write the multiplication with a cross. We just write A, B for A times B. Now, in the examples, in the matrix algebra, mat n, a matrix A is invertible, in other words, satisfies this property precisely when its determinant is non-zero. That's a key result of linear algebra. In the complex numbers, the story is the following. In the blue complex numbers, a vector xy is invertible precisely when x squared plus y squared is not equal to 0. In fact, that's also a determinant. That's the determinant of the matrix x, y minus yx. So it's really a kind of a special case of this thing here. And similarly, in the red complex numbers, xy is invertible precisely when x squared minus y squared is not equal to 0. That's the determinant of the matrix x, y, yx. And finally, in the green complex numbers, xy is invertible precisely when x times y is not equal to 0. That's the diagonal, the product of the diagonals, which is the determinant in that case. Okay, so what makes the blue complex numbers particularly sort of familiar to undergraduates and important is that this algebra is a field, and what that means is that, in fact, every non-zero element in the algebra is actually invertible. So this condition applies to all the elements in the space except for the 0, 0, 0 vector. That's not the case with these ones here. You can check, you can find non-zero elements that are non-invertible. But I don't want to actually go in that direction of a field, because it's not the concept of a field that I'm really interested in here today. It's the concept of an algebra. So while the invertibility will play a very important role, we do not insist that everything except for the origin is invertible. We just have an algebra, then asking what are the invertible elements is a very natural step. So now let me introduce the main objects of today's lecture, which are these algebras called K-poly algebras. Okay, and there's one for every natural number k. And they are very closely connected to the algebra of polynumbers that we've worked with a lot in the Algebraic Calculus 1 course and also in the Algebraic Calculus 2 course. But they are different. Okay, so what's the definition of the K-poly algebra? So choose a k, a natural number, including 0, so 0, 1, 2, 3, or whatever. So then here is what an element in this K-poly algebra looks like. It is a list, a vertical list of numbers, rational numbers, a0, a1, up to ak, okay, enclosed in this kind of bracket kind of border. A line on top, a vertical line beside, a line on the bottom. So that's what a K-poly is. In this case here, actually, it's a K-poly because we're going down to k here. So altogether, there's k plus 1 elements in this K-poly. Now here's another K-poly, B, with entries B0, B1 down to BK. So the first order of business is to just say what is the linear structure, and that's the obvious thing. We're just thinking of these as column vectors. So the addition of A and B is just pointwise, and the scalar multiplication is also just pointwise. So that's very familiar. And now we come to the multiplication. Now this multiplication will look familiar to you, but I want to emphasize that this is really a new thing, even though it is very, very close to the arithmetic for polynumbers, but it is essentially different. So what is the product of this K-poly with this K-poly? A times B, what is it? Well, it's another K-poly. Okay, it's another K-poly. And the 0th element is A0 times B0. The 1th element is A0 times B1 plus A1 times B0. The 2th element is A0 times B2 plus A1 times B1 plus A2 times B0. Hey, you're saying this is just the way we multiply polynumbers. You're absolutely right. It's exactly the same. But we go down to level k. So the entry at level k here will be A0 times BK plus A1 times BK minus 1, all the way down to, say, AK minus 1 times B1 plus AK times B0. So the sum of these indices is always k in this kth row. So now what makes this different from the algebra of polynumbers? The difference is that we stop right here. Okay, we stop and we have this border. Okay, so there's a border up on top, side border, and then there's this border underneath, and that's finished. Now it's done. Now if you were going to multiply these two things as polynumbers, you would not end up here. You would have to keep going, because the next one would be sort of total sum of degrees is k plus 1. So you could get a1 times bk plus a2 times bk minus 2, etc., all the way up to plus ak b1. But that term is not involved here. So now it's a natural question. Well, is this really an algebra? So this is a great exercise to stare at this and to convince yourself that it is an algebra. And at some level, it's kind of obvious, because if you think about the way you multiply two polynumbers, right? So imagine having a polynumber here and a polynumber here, and we've chosen sort of a level k. What we're doing is we're just ignoring everything below that level, okay? And we know that when we multiply polynumbers, say like this level here, the two level of the product only depends on the polynomber ingredients up to level 2. So if we want to know what the level 2 guy in the product is, we only have to look at the entries A0, A1, A2 from this one, and B0, B1, B2. So we just disregard everything else. And it's this fact that makes it reasonably easy to check that this really is an algebra. I also ought to say right at the beginning here that these algebras are commutative. Okay, that's an important consequence of the law for multiplication that I just gave you. If you look at it, it's symmetric. If you interchange the A and the B, k polys, then each entry is still the same. You're just sort of reading it, instead of reading from left to right, you read it from right to left. So let's do some arithmetic, say with 2 polys. Okay, so a 2 poly has 3 entries. So level 0, level 1, level 2. So here are two polys, 2, 1, minus 3, and 1, 0, 5. So the sum is, of course, just the pointwise sum, 3, 1, 2. And multiplying it by a scalar is, of course, obvious. If you wanted to multiply this thing by a scalar 4, you'd get 12, 4, 8. Okay, what about the product of these two? So 2, 1, minus 3 times 1, 0, 5. Okay, so here's the product. The 0th entry is 2 times 1. The 1 entry is 2 times 0 plus 1 times 1. The 2 entry is 2 times 5 plus 1 times 0 plus minus 3 times 1. And that amounts to 2, 1, 10 minus 3 is 7. Note that this is different from the product of these polynumbers. If you rubbed off that bottom bar, okay, and then they'd be polynumbers, then you would have to add some more terms. Okay, so the next term would be 1 times 5 plus minus 3 times 0. That would be 5, so there'd be an extra 5. And then there'd be one past that, minus 3 times 5. There'd be a minus 15 as well. Okay, but they are not being involved. This 2 poly times this 2 poly is this 2 poly. Okay, it's pretty easy to check that the identity is what you think it should be. It's the poly 1, 0, 0. And here is a very interesting exercise. Okay, very interesting exercise. I really want you to do this. Show that this 2 poly, say A0, A1, A2, is invertible precisely when A0, the top entry, is non-zero. Okay, so you can obviously then generalize this to a k poly instead of just a 2 poly. And a more subtle thing that I want you to start thinking about is, okay, this thing is invertible. What then is its inverse? Okay, that's going to be a really important problem for the algebraic calculus. Okay, so let's now talk about the standard basis of the k poly algebra. There's a standard basis. And it all rests upon this fundamental k poly, the one that looks like 0, 1, 0, 0, all the way down to the bottom 0. So this is just like alpha, playing the same role as alpha does in the world of polynumbers. But I remind you that for alpha, and in the world of polynumbers, we were not fussed about these following zeros. We allowed ourselves the flexibility of being able to add zeros at the bottom of a polynumber or remove them. Okay, it's not changing the polynumber. Here with these k-polys, we're going to be much more fussy about that. We're going to insist that there's exactly k plus 1 entries in this list. So we are not allowed to rub off any of these zeros. They are an integral part of these objects. Okay, so they behave a little bit different from polys. So since this is not the same as alpha, even though it looks pretty close to it, let's give it a related name. Let's call it alpha sub k. Okay, because it's a k-poly. There's altogether k plus 1 elements here. So if that's alpha sub k, then alpha sub k squared will be 0, 0, 1, and then a bunch of zeros. And carry on, alpha sub k to the k, the last one, will be all zeros with just a 1 at the bottom. And then to be consistent, well, what about the case when there's just a 1 up at the top? Well, let's call that alpha sub k to the 0. So then we have a basis. Alpha sub k to the 0, alpha sub k to the 1, alpha sub k squared, all the way up to alpha sub k to the k. Altogether, k plus 1 elements in this basis. So then, for example, here's a typical k-poly. Say a equals a0, a1 down to ak. We can then write that as a linear combination of these basis vectors. Start with this one here. So it's a0 times alpha to the k0, that one there, plus a1 times this vector, all the way up to ak times this vector. So this just sort of corresponds to the obvious, usual, familiar, standard basis for column vectors. But now these have sort of interpretations as powers of this alpha sub k. So we could rewrite this thing as a0 alpha sub k to the 0 plus a1 alpha sub k to the 1, or just alpha sub k, plus a2 alpha sub k squared, all the way up to a sub k times alpha sub k to the k. Now, we are going to have to observe one more thing about this alpha sub k, this element here, that if we raise it to the k plus first power, then we get 0. Okay, this is the 0 vector. So why is that? So here's alpha k, and here's alpha k to the k. What happens if we multiply those? Well, what you do is you're going to calculate these products, but you're never going to get, there's only a single 1 in this case, there's only a 1 in this case, and none of these products that occur in the expansion will have the product of this 1 times this 1. So every single entry of the product of this one with this one will be 0. So this is a very different property that alpha sub k has from the usual alpha. Now, we will sometimes, when we're knowingly working in k-poly, we might not want to write these subscripts all the time because it gets kind of tedious to keep writing alpha sub k. So I'm going to introduce a shortcut for that. Okay, but the shortcut is not alpha, because then there's possibility of confusion with the polynumber story. Here's what the shortcut is going to be. We're also going to just call this epsilon. When you see epsilon, maybe you think about an infinitesimal. And if you've watched my famous math problems lecture on how to set up infinitesimals, you will probably twig, why we're doing this. That this element here is a potential infinitesimal for us in our differential calculus, as we will see. Okay, and now let's introduce truncations. But we're going to have a little bit of a different spin on truncations than we did last time we talked about this. So we've talked about truncations t sub k, and the idea there was that truncation is, you take a polynumber and you just truncate it. Terms up to a certain degree and then no more. So we're going to be doing something very similar, but the shift is important, okay? We're going to now think of this truncation operator t sub k as going from the algebra of polynumbers, or poly, to the algebra of k-polys. And it's defined as follows. So t sub k, here's a polynumber, a0, a1, down to some a sub l. Now l could be bigger than k, it could be smaller than k. It could be equal to k. It doesn't matter. What we're going to do is we're going to truncate this thing. We're going to take the top k plus 1 elements here, so a0, a1, down to a sub k, and then we're going to stop. So we're going to put a bar underneath to ensure that we get a k poly and not a poly. So I must say that we potentially may need to add zeros because we have to go all the way down to the bottom. So in other words, let me illustrate with this example here. So here, let's work in the world of 3 polys. Okay, so 3 polys have 4 entries, 0, 1, 2, 3, 4. So here's a poly number, 1, 14, minus 2, 6, 17. Let's take t sub 3 of that. What we do is we strip off the 0th one, the 1th one, the 2th one, and the 3rd one, and disregard everything else and just put a bar to close things. How about t sub 3 of the poly number 5 minus 7? So I remind you, in the world of polynumbers, 5 minus 7 is the same as 5 minus 7, 0. It's the same as 5 minus 7, 0, 0. So we're going to use that intuition to just copy this thing, but copy the first k plus 1 entries, in this case 5 minus 7, 0, 0. So 4 entries because we're starting at 0 and going up to 3. So it means we have to sort of add 2 zeros so that we have the right number of entries here, so we really have a 3 poly. Okay, so here's the truncation theorem, which justifies our usage of this truncation operator. It's that if p and q are polys and k is a natural number, then the truncation t sub k of the product p times q is the product of the truncation of p times the truncation of q. And another way of saying this is that t sub k from poly to k poly is actually an algebra homomorphism. So this is cleaner than the last time I talked about truncations, where we were just working in the context of polynumbers, and there we had to truncate again on the right-hand side to make things work out. Going into the world or the algebra of the k polys means that we have a cleaner sort of algebraic structure. So let me illustrate here. So here's, let's say, t sub 2. Here's 2 poly numbers, 2 minus 1, 1, 0, 3, minus 4. The product of these two things is, I guess, 2 minus 1, 6, minus 11, 4. So let's take t sub 2 of this. What does that mean? Well, we just take the 0th element, the 1th element, and the 2th element, and stop there to get this 2 poly. 2 minus 1, 6. And now we want to convince ourselves that this is the same as t sub k of p times t sub k of q. So what's t sub k of p? The truncation of this one, 2 minus 1, that'll be 2 minus 1, 0. We're taking t sub 2, so we end up with a 2 poly. The truncation of this q is 1, 0, 3. And so now these are, in the world of k polys, let's just check that we get this. So 2 times 1 is 2. And 2 times 0 plus minus 1 times 1 is minus 1. And 2 times 3 plus minus 1 times 0 plus 0 times 1 is 6. And that's all there is. So this is indeed correct. This really is t sub 2 of 2 minus 1. This really is t sub 2 of 1, 0, 3 minus 4. And that illustrates this algebra homomorphism property. So we've done something which, in some sense, it's very elementary and familiar, but it's important to, first of all, appreciate the importance of this algebra structure, okay, and that we're aligning things so that sort of algebraically things are working nicely with respect to these truncations. It's going to be really helpful for us as we move further on into the differential calculus in the Algebraic Calculus 2 course. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.